All right, well, welcome everyone to Free Heat, heating and cooling buildings entirely with ambient energy. And this is volume 3 of our passive solar series, which started in 2022, I believe, at the end of the year, 2022. We started with part one, the basics of passive solar. And then earlier this year, we did part two. For our I guess you could call it our 201 session in passive solar, our advanced session. This is our expert session in passive solar. So if you haven't watched the other two, that's okay. It's not that they're required to watch in any order. But if you're watching this recording or watching this later on, you might want to go back. And if you're not too familiar with the concepts of passive solar, go back and start with the basics, go to the advanced, and then watch this one as the more expert session on passive solar. But again, you're welcome here, and we want to engage everybody at all areas. So this is real exciting because here's the deal when it comes to passive solar. It really is free energy. We have seen it with our project teams. We have seen homeowners share this information, especially as it gets colder out, sharing how their heating isn't even running. Their heating systems don't even need to be turned on, even to the point where some people have to open a window to cool the home down in the dead of winter. And so it is real. This is real stuff. We've seen it with our own eyes. We know it can be done. And now putting some methods to it is real exciting for me. So with that, before we get started, we always need to say a special shout out to those who support the Green Home Institute. So I want to say a special thanks to Build Equinox. Traditional ERVs and HRVs provide basic ventilation, but often lack protection against airborne threats like seasonal flu and wildfire smoke. So now we have the CERV, CERV, an advanced indoor air quality management system. It offers energy recovery ventilation along with enhanced protection and intelligent air management. Continuously monitoring CO2, VOCs levels helps ensure fresh air is only brought in when pollutants exceed healthy standards, improving indoor air quality and saving energy. Features a high efficiency heat pump that recovers the energy from exhausted air, preconditioning and dehumidifying incoming air for comfort. It operates in recirc mode, acting as a whole house purifier when providing dehumidification and supplemental heating and cooling, as well as an optional UV light if you're concerned about other air quality risks. You can visit buildequinox.com to learn more about the Serve and its enhanced indoor air quality components, as well as the new Serve 1000 for more commercial and classroom settings. All right, so this course is brought to you by the Green Home Institute. The Green Home Institute is a nonprofit with a mission to empower people to make healthier and more sustainable choices in the renovation and construction of the places we live. Today, I will be your moderator. I am the education manager here at the Green Home Institute. And as always, our courses are approved for multiple continuing education units, including the three pillars under our Certified Green Home Professional designation: health, materials, and energy. AIA Health, Welfare, and Safety may make it applicable to your state-based design or contractor license. Check out the 5-digit Passive House code after you've completed this session. You'll see it printed on your certificate as well, as long as you've been here the entire CU approved hour. So with that, I want to welcome back Keith Sharp. Keith was a guest speaker on our advanced solar session earlier this year, giving us a hint, a glimpse really, at what ambient energy is. But now we have him back for the full session, and I'm very excited to welcome you back, Keith. I appreciate your time. Please take it away.
Thank you, Brett. I am Keith Sharp. I'm an emeritus professor from the University of Louisville and uh, have done research on buildings that are entirely conditioned by ambient energy for decades now. Um, Let me see here. Okay, the header went away. That's good. Okay, so we have known for a long time about this coming problem of global temperature increase. Back in 1893, Svante Arrhenius did some modeling and showed that doubling atmospheric CO2 would increase global temperatures by 5 to 6 degrees Celsius. And we are more than halfway there to doubling CO2. And it's only because the time constant of the Earth is around 9 years that we haven't reached half of that 5 to 6 degrees Celsius. If we stopped increasing atmospheric CO2, temperature would continue to increase for several decades. So we need to do something. IPCC says that we need to reduce carbon emissions to zero by 2050 to limit global temperature change to 1.5 degrees C, and it's looking less likely that we're going to meet that target. We don't have to look to the future to find problems. 2 million human deaths and $4 trillion in damage has occurred in the last 50 years, and at least part of that is attributable to the climate change that we have already. So the inescapable conclusion is that we need to eliminate fossil fuel combustion as soon as possible. So about half of our energy is used in buildings, and that's a result of adding up the residential and commercial sectors and a part of the industrial sector, the buildings in the industrial sector. So buildings are a big part of the problem. But if we categorize the energy differently, separate out all of the energy that's used in thermal form, like heating and cooling of buildings, that's about half. So alternative sources for thermal energy are key, and ambient sources are great for doing that. In buildings, we use fossil fuel directly in the black and gray parts of these bars, but we also have to remember the blue bars, which are electricity, currently are also 60% fossil fuels. So there's a lot of fossil fuels that we need to replace. And solar energy is the obvious source for heating. And even in Fairbanks, Alaska, almost 10 times as much energy strikes either a horizontal or vertical surface of a building in the form of solar radiation than the building uses. Those small blue bars out on the right-hand side are residential and commercial energy use over a year. And heating from the sun is simplest done by passive solar heating. And Brett mentioned Debbie Coleman's first part of this series, and you can review some of the guidelines there. Those guidelines still work for the advanced ambient conditioning. I'll mention where the guidelines are a little different. So direct gain is simply south-facing windows. You do want to have special windows that are high solar heat gain constant. Indirect gain comprises putting a thermal mass between the south windows and the living space. And then a sun space, we just widen that space so we can grow plants there, or it's a pleasant place to read a book in the wintertime. And isolated gain is the more complex system that is actually the highest efficiency, and that is a solar collector that is below the living space so that it thermosiphons to the living space when the sun is out. Other ambient sources include ventilation air, which can come in at a higher or lower temperature than indoors. Potable water usually comes in cooler. We have internal heat gains. The sky is a cold sink, and we can have either losses or gains to ambient air. Wastewater, especially that hot water that we use energy to create, we can recover that heat before it leaves the building, and we can have losses to the earth. And here's an example for Louisville, Kentucky. The comfort ranges are the red horizontal line for the high limit and the blue limit for the lower comfort temperature. And we have air at monthly high temperature and monthly low temperature in the blue and red curves. Wet bulb temperature is not a lot different from the low monthly temperature because this is a relatively humid climate, but evaporative cooling can work a lot better in dry climates. Ground temperature is typically in our temperate climate zones lower than the comfort range, and so it can always be used for cooling. And then night sky, notice that's the lowest temperature of all, so it has a lot of potential for cooling. So we are talking in this presentation mostly about space conditioning, heating and cooling, but dehumidification can also be done, especially with sky radiation. If we can get air down to 14 degrees C or 57 degrees Fahrenheit and condense out the liquid, so it's 100% relative humidity, that air, when it's warmed up to 22 C or 72 degrees F, is at a comfortable relative humidity of 60%. And Zach Springer's paper talks about doing this with sky radiation. So we can also cool from the air, and this cartoon shows the stack effect where hot air rises and cool air replaces it. We can also get cooling by the wind with cross ventilation. We can cool and heat from the ground. So on the left-hand side is the cooling mode. In our temperate climate zones, the Earth down low enough is usually between 50 and 55 degrees Fahrenheit. And by circulating either liquid or air in a ground heat exchanger, we can directly cool the building. We can also use the ground for preheating. When it's really cold in the air, we can send liquid or air into that same heat exchanger and get it up to a temperature that isn't as warm as the inside of the house, but it can be used for preheating. Cooling to the sky, the classic example is Harold Hayes' roof pond house. This is the prototype from 1967, and there's a layer of water on top of the building. And then on the left, there is a sliding panel that during the night, it is slid off to the left there, and the water radiates to the sky. Then during the day, when you want to avoid heating the water by the sun, that panel slides across the layer of water. Now, you don't necessarily need to use a layer of water. You can use sky radiators and thermosiphon between the radiators and a lower storage. Thermosiphoning works well because the radiators are cooling the liquid and it naturally drops down to the lower storage. And then when the radiators get hot during the day, the hot water just stays in the radiator. So compared to a conventional house where we keep the temperature relatively constant with as much auxiliary energy as necessary, and right now with an all-electric grid or an all-electric building, that would be with electricity, which currently is 60% derived from fossil fuels. An ambient house keeps the temperature between a low and a high limit with ambient energy only. And to do that, we use a hot source and a cold source and regulate the heat transfer between those sources and the house. And then when the appropriate source is not available, we use thermal mass to moderate the temperature swings until that source that we need is available again. So here's some examples of houses that are more or less 100% ambient conditioned. Maria Talkas, back in 1948, built a house that was 100% solar heated for 2 winters. And this is actually an active system where air is blown through those collectors that are very large. They're on the upper floor of the building. Harold Hayes followed up his prototype with a full-scale house in 1973. It's again a roof pond house. Paul Shippey built a house in Longmont, Colorado in 1978 that's earth burned. So that reduces the losses, and you can see there are lots of south-facing windows. Carl Warren built a Norm Saunders design in Boxborough, Massachusetts in 1986, and that house is still lived in. It has remained between 65 and 75 degrees Fahrenheit for all these years. Really top performing house. And then 2 more modern houses. Jim Riggins' house in Monument, Colorado in 2011 is almost 100% ambient conditioned. And we'll talk more about my house. And the references below, my paper in Solar Today talks about all 6 of these houses. And then Jim Riggins just recently did a nice YouTube video on over a decade of performance for his house. So those of you who don't like math can take a nap for one slide. Here, we're trying to identify the simplest model that we can use to quickly get some results for a house to make it 100% ambient conditioned. And these equations have all the terms that I think are important without any extra ones. For ventilation cooling, on the left-hand side is the thermal capacitance times the time rate of change of temperature. And then on the right-hand side, the first 2 terms are the gains. The first term is the solar gain. G is the internal heat gains. And then the last 2 terms are the losses, the envelope losses, and the ventilation cooling losses. We have a similar equation where just the last term changes for sky cooling. It gets more complicated because temperature is to the 4th power, but both of these equations have analytical solutions, which allows us to get a result very quickly for hourly temperature. Now, there are similitude parameters that arise from these equations. The first being the solar load ratio, which you probably heard of from the Balcom era of passive solar. There's also the internal heat load ratio, which is the ratio of internal heat gains to envelope losses. The thermal time constant, which is the thermal capacitance of the building over the envelope losses. And a ventilation to load ratio, which is the ventilation cooling to the envelope loss coefficient. Now, if we're using sky cooling, then there's a similar sky cooling to load ratio. And we also have some control parameters in the model where F sub S regulates the shading of solar gains. And then depending on whether we have ventilation or sky cooling, there's a control parameter that turns on and off that cooling. So everybody come back now. We're going to show that same energy balance in a cartoon here. The 2 gains are solar heat gains and internal heat gains, which we're modeling as a flow of water into a bucket that represents the house. The house is comfortable as long as we have some water in it. If the bucket is empty, that is like the house getting cold, or if the bucket is overflowing, the house is overheating. And then we have losses with our passive cooling and also envelope losses. So those similitude parameters, with the Buckingham pi theorem, we can reduce those 5 to 2 non-dimensional ratios. The first one is the ratio of both the gains over both the losses, and pi 2 is that thermal time constant. Now, pi 2 is a little complicated, so to understand which parameter is doing what to the performance of the house, it's good to break pi 1 into 3 parts: the solar load ratio, internal heat load ratio, and then our cooling to load ratio. Okay, so a very important concept for designing a house to be 100% ambient conditions is that indoor comfort depends on bridging of that usually one, most extreme event of the entire year. So in this graph, we have solar gains in the gray peaks and then indoor temperature in the green curve. And this happens to be for Durango, Colorado. And over 10 days, we have 7 cloudy days. This is the most extreme weather event of the entire year. It's also cold during this time. And the house reaches its lowest temperature at the end of this period. And we are designing the house to remain comfortable, in particular for that one lowest temperature. So it makes sense that we need to simulate the house and get hourly temperatures for the entire year to find that one most extreme event. So again, we need to use what's called a dynamic model that gives us hourly predictions of indoor temperature. So static models neglect the thermal mass for the most part and give an instantaneous response to temperature change. And examples include PHPP, woofy passive, ecotrope, and HEAD. HEAD uses an admittance method which approximates the effect of thermal mass, but we have better options available. So we're going to say these are not appropriate for ambient house. Dynamic models, yes.
Keith, yeah, there was a quick clarification question if you can, and maybe it'll help here. Is the question was, can you define the thermal capacitance?
Yeah, so thermal capacitance is the mass of the building times the specific heat. So just the multiplication of those two factors.
Yeah. Okay, thank you.
And thanks for the question. So dynamic models in their complex and general form include BLAST and DOE2. They're grayed out because they're legacy programs that aren't available anymore. If you still have a copy, they work great and you can use them for ambient condition buildings. What's available now is programs like Energy Plus and Transys. And more simplified models include Energy Plus, Energy 10, sorry. If you still have a copy, a lot of people really like this program. What's available now is BOPT, eQuest, and Woofy Plus. And I actually used BOPT and Woofy Plus to design my house along with my own program and compared the results. A really interesting one was developed by Professor Troy Peters called Solar Shoebox. And it's designed from the beginning to use only ambient energy and to simulate what's called a free running building that doesn't have a furnace or air conditioner. Now, we should also talk about the solar load ratio. These were curve fits of a dynamic model, but they used 1980s insulation and 1980s windows, and they only give monthly results. So again, we have better options available. Now, we should also mention, yes, you
One
had a
quick
question?
Yeah, so for those who don't know, the Woofy program is a modeling software needed for the Passive House US FIAS certification. And I'll admit I didn't know I knew there was a free version and a paid version. Is the free version the passive and the paid one the plus? Is that why you get more? Is that incorporating all the stuff in passive, or can you briefly describe that?
Woofy Plus is a dynamic program and it is also free, or at least it was when
Oh,
I used it to design my house.
uh-huh.
And some of the limitations are you you get figures of the predictions or the graphs of indoor temperature that have Woofy Plus across them.
Yeah.
And if you pay, then you can get a few more features including um, hygrothermal
Yeah.
modeling, which isn't in Woofy Plus.
Right. And
Woofy Passive,
that's what's required for a passive house certification for passive house. So there must
right.
be two
And
different softwares, but I'd imagine the highest level one would be a dynamic one that also models everything. But maybe some of our
yeah,
passive house folks here can explain it a little bit better. Do you know PHPP, when's the last time you checked? I had thought that one had progressed to a dynamic model, but maybe not.
you may have more current information than
Yeah.
I do, but
Yeah.
the last I looked at, PHPP just gave monthly results,
Yeah.
and uh, we tried it with designing my house a couple of years ago, and
Yeah.
it did not give hourly indoor temperatures.
Okay. Yeah, maybe someone can clarify if it's been amended. But anyway, thanks for clarifying that.
Okay, thanks for the question too. So PV watts is for photovoltaic design. It's not for ambient houses. But the great thing about it is it only takes 6 inputs. You can literally get results from PV watts in a couple of minutes. You have to choose the weather data that you want to use, and then there are 6 inputs that are really simple. Wouldn't it be great if we had a similar program to calculate the performance of an ambient house, not necessarily really in a lot of detail, but just to get some targets that we can use as we're designing the house? And there is such a program, but it's not quite ready for public use. It's my program that I tentatively called ambient watts, but I'm thinking more and more about calling it free heat in honor of Byron Wynn from Colorado State University. So here are the 5 pre-designed parameters that you have to put in. The first is the envelope loss per unit floor area, and there's a recommendation that is given that meets the passive house limit of 10 watts per square meter of peak losses. So you have a value that you can just plug in there and see how it works for the first iteration. The second is internal heat generation per unit floor area. There's a passive house default that you can plug in there. Now, this is a value that comes from European houses, and I think in the US we use a little more, but there's a value that you can use for the first time around. Net transparent glass area for solar gains, 5% is a good place to start, and you may need more in cloudier climates. And then the mass per unit floor area, there's a range from light to heavy conventional construction, and I'd recommend using something, say, right in the middle of that range. And the final one is the ventilation cooling to envelope loss ratio, that VLR. And 9 is something that you can easily get to with operable windows, and you could potentially get quite a bit higher, but 9 is a value that you could use, and it works in a lot of temperate climates. So there I've described all the inputs in just a minute or so, and the results come back in a fraction of a second because of that very efficient analytical solution. And I'll show the predictions for some example houses a little bit later. So there is a program that I wish was available on a website, maybe on NREL's website right next to PV Watts.
Keith, what you had mentioned this is not ready. What is still under production to where this might be something usable, or is it just that you were hoping it's, as you mentioned, a federal tool that's available?
Yeah, I would like it to be publicly available, like right next to PV Watts. The biggest problem now is this program is in Excel, which does not have the capability of downloading weather data
Ah,
from site, like from the National Solar Radiation Database. The other problem is that we need special weather data that is also not yet available. And that's part of what I'm going to describe a little later.
oh, fair enough. Yeah, I'm eager to hear.
Okay. So there is a new approach. So the old passive solar buildings had a lot of solar gain. And up on the left-hand side, there's Carl Warren's building. You can see there is a lot of glass. Um, and the envelope losses were low for the time, but now we can do a lot better, which meant that with those large solar gains and large envelope losses, you needed a lot of thermal mass. This house, if Carl is listening, he can correct me if I'm wrong, but I think it had 18,000 pounds of water in an upper storage unit in the attic and 100 tons of gravel under the floor. So the modern approach is to have much lower envelope losses, which means you can get by with smaller solar heat gains and smaller thermal mass. It's actually in the range of conventional construction. So let's take a look at some of those numbers. The peak load is now, for the 2 more modern houses, is down in the range of that passive house standard of 10 watts per square meter. The 4 older houses are quite a bit larger than that. The internal heat gains were for the older houses something that you could perhaps neglect because they were pretty small. But now, if you're talking about 2 to 3 watts per square meter and the envelope losses are 10, then that's something that you really can't neglect. So much different for the modern houses. Light to heavy conventional construction is like 100 to 400 kilojoules per square meter per degree Kelvin. And you can see that the two modern houses are within that range, but the older houses are well above that. Solar aperture as a percent of floor area is now less than 10% for the modern houses, but it was up to 100% for the older houses. And then here's where we can use those similitude parameters. If we add the solar load ratio and the internal heat to load ratio, those are our two heating sources. That needs to be in the range of 1 or a little bit more. And you can see for all of these houses, even though the designs are very different, they are all within that range. And then finally, the thermal time constant is 1 to 7, except for the Telkis building, which used phase change storage. It's much higher. A larger time constant is useful in every climate, but it definitely needs to be higher in the more cloudy climates like the Saunders house in Massachusetts. And the ventilation load ratio, as I mentioned, 9 worked for all of these houses, and you may need something larger for hotter climates, which we'll talk about a little bit later. Okay, let's, yeah, question?
Can you
Brett?
elaborate again just the term ventilation load ratio? That's just the load being drawn down on the house with the ventilation, or can you elaborate a little bit more?
Yeah, so the ventilation to load ratio is the ratio of the ventilation cooling coefficient to the envelope loss coefficient. And
Okay.
9 means that by opening windows, we are increasing the losses from the house by a factor of 9. We also have the envelope losses at the same time. So
Right.
together, those will be 10 times greater losses when we're intentionally trying to cool the building down.
Right. Okay. Thank you.
Okay, so this is the south side of my house, and as you can see, it's a really cold climate. It's 8,000 degree Fahrenheit days, so that's really cold. Um, Inside, the house looks pretty normal. You can see that in the window sills, there's a lot of thickness in the walls that's filled with insulation. What looks like a wood floor is actually a tile floor over concrete. And then in the basement, there are concrete perimeter walls and a concrete slab for thermal mass. The only auxiliary heating is the fireplace that you can see there on the left. And the house has an ERV by Zender, and it also has a ground loop heat exchanger. That's the unit that is just to the right of the ERV. And then on the right-hand side, you can see the trench that was dug for the pipe that connects to a heat exchanger in that ground loop unit. And here's a picture of the Larson trusses going up. Those Larson trusses are kind of like eye joists that you attach to the structural stud wall. And they are 16 inches thick. That's all filled with insulation. And then on the outside, you can see part of the OSB has been installed. The air barrier is the green zip sheeting, and then you can see the four-sided window bucks that extend the air barrier out to the window. And the overall characteristics of the house are shown on this slide. We are really close for 2022. The peak loss depends on the weather, so we have to specify a particular year to that passive house limit of 10. And the internal heat gains are measured from energy bills for 2023, and that was 2.4. That was lower than the value that we used to design the house. So that means that the house is going to be cooler than the predictions. Solar aperture is 6% for the gross window area and 4% for the net transparent area. Ventilation load ratio was 6.8 based on an aperture or orifice model for the loft windows being tilted. They can also be fully open to make that ratio even larger. We use 9 for the design value, so we're good with cooling. Thermal mass again is kind of in the middle between conventional light and heavy construction. And the similitude parameters. The solar load ratio for January for 2022 becomes 0.6. And in January internal heat load ratio 0.4. So we're right at that good value of 1. And then the thermal time constant for 2022 for the entire year was about 1.7. And here is the latest measurements of indoor temperature. We don't have archived data yet, or actually it may be available now for 2023, but it takes the National Solar Radiation Database about 10 months to archive data from the previous year. So we don't have modeling results for 2023 yet. And the comfort limits are in red and blue here. And you can see in the first month, in January, we have some times where the temperature is below our lower comfort limit. We'll show that in a little more detail. A few hours in February also, but the rest of the year stays within the comfort limits. So for heating, again, we have 2 windows that are direct gain that we saw from the inside also. And then those lower 3 windows are a trom wall. We have some other south-facing windows. Some of those are shaded just because of architectural decisions. We have some east-facing glass also that provides a little bit of gain. And here we're taking a close-up look at January performance. We had a fire in the fireplace for the 1st of January and then a couple of times later in the year. And you can see those times when we dipped below the lower comfort limit. Almost all of those times are within 1 degree Celsius, but there are a few hours that are in the 2 degree Celsius bin below the comfort limit. And for cooling mechanisms, those upper loft windows are those 3 windows above. They can be tilted or fully opened. And then we also open some lower windows to complete the circulation. And for 2023, we installed shades on the trom wall, which just anecdotally, I think those helped keep the house cooler. And this is the cooling season. From July to November, these are the temperatures that remain within the comfort limits. And I want to show you the manual operations that we had to do to keep the house cool. First, around the 1st of July, we tilted 2 of the loft windows. We didn't think we needed the full capability of ventilation cooling, so we just tilted 2 of them. A little bit later, as the house started to warm up, we tilted the 3rd one. The house cooled down. The ground loop was completed near the 1st of August. That operates automatically, so no further interaction was necessary for that. The trom shades were installed as the house started to heat up a little, and they were removed as the house started to cool down there in July, around the end of September. And then we finally closed the loft windows in October. We also opened lower windows. And when the house got especially hot, we opened and closed those every day. The loft windows, because they're hard to get to, were left open for the entire cooling season. So internal temperature histogram is shown here, and you see almost all of the hours are comfortable. We do have 260 hours or 3% of the year where we have undercooling. Almost all of those are in the 1 degree Celsius temperature band and just a few in the 2 degree temperature band below our comfort limit, and there was no overheating. So pretty good performance of this house, in spite of the mistakes I made in design. Indoor temperature swings is a question that often comes up, and they are between about a half a degree Celsius and 2.5 to 3. The average has been 1.5 or so degrees Celsius or 2.5 degrees Fahrenheit. There is in the spring much lower temperature swings, and I think that's because the sun angles are increasing, so the solar gains are not as great, and we haven't yet opened windows for ventilation cooling. So the house is just sitting there pretty isolated and results in lower temperature swings. So for summary, the house was for 2022 or 2023 was 99.7% ambient heated, a little bit of wood, 100% ambient cooled, and we used just under 5,000 kilowatt hours for the year, or that's 21% of the average residential building. And the weather for this year had above average January cloudiness. And if we were to try to address that with the design of the building, we would use more thermal mass or more insulation. More solar gain wouldn't work because, after all, it's cloudy outside. Improvements in 2023 included the sunshades for the trom wall, which I think cooled down the building a little bit. And we also got the ground loop installed for the ERV. Future plans include insulating the attached garage, which is on the west side of the house, and that will reduce the losses out that end of the house. Okay, so let's look at another design. This is a pre-design. This house has not been built, and it's for Habitat for Humanity in Pagosa Springs. Now, the first question when you're designing a house to be 100% ambient conditioned is what weather data to use. Now, TMY, or typical meteorological year data, is often used for conventional buildings, and it actually works well for getting kind of an average result. But heating and cooling equipment is oversized to accommodate years that have more heating load or more cooling load. So a better example for designing an ambient house is from Maria Telkes. She studied 65 years of real weather data and found that the longest period of cloudy days was 9. So she sized storage for 10 days. So a little safety factor there. We're going to do even better. We're going to use a building model-based selection of weather data so that we can have reliable performance over a long period of real weather. So in this slide, we're going to show what happens if you use TMY weather data to design an ambient condition building. So if we use TMY 2020 to design a building to remain comfortable for that weather data set, and then simulate it for every year from 1998 to 2020, those are the years that are used to develop that TMY data set, we find that all of the red bars there, the building overheats for that year. So it's more than half. Maybe that's what you might expect if TMY represents an average year. But let's take a look at Phoenix. If we design a house with TMY 2020, it only overheats for 1 year. We got really lucky there. The client, if you designed the house with TMY data, would be pretty happy. Just 1 year that it doesn't quite meet the expectations. But now in Madison, Wisconsin, a cold and cloudy climate, if we design with TMY, we get a building that undercools for all the blue bars, overheats for the red bars, and does both in the same year for the purple bars. So your client, if you designed with TMY, would be pretty unhappy every year. Rock Springs, a cold and sunny climate, we get a lot of undercooling and 1 year of overheating. So I hope this convinces you that TMY is not the right weather data to use for 100% ambient conditioned house. Well, what are we going to do then? We're going to develop an ambient meteorological year that comprises selecting the worst winter and adding on to that the worst summer. So we've got 1 year of weather data that will give us the extreme in performance of the building. And if we design it with that weather year, we can have some confidence that the house is going to be comfortable for many years of real data. So for Pagosa Springs, we're going to do that. We're going to use just a generic passive house design. Doesn't have to be exactly the house that you're going to build. It just needs to be relatively close. And we're going to use these runs where we're running every year from 1998 to 2022 and finding the worst heating year and the worst cooling year. So here you can see that 2017, the house got to its coldest indoor temperature. And it's hard to see, but 2003 was the worst summer. We're going to assemble a year from the winter of 2017 and the summer of 2003 and use that to design our habitat house. So the mission of Habitat for Humanity is to provide affordable housing for low-income clients. And what better way to do that than to also zero out their heating and cooling costs? Now, habitat houses are usually small, and this example house is going to use a 1,000 square foot floor plan. That may be a little bit large for the group here, but it's going to be square. And in the graph here, square provides the lowest wall to floor area ratio. So it minimizes the materials that are used and also reduces losses compared to, for instance, for a 4:1 rectangular floor plan, it has 25% more materials in the walls and 25% larger losses. Now, circle would be even more efficient, but that's more difficult to build. So the inputs for my program, we're going to use 16-inch polystyrene insulation around 8-inch concrete structural walls. Why would we do that? Geofoam, you may have heard of that, comes in large 16-inch thick blocks, and it's easy to attach to the concrete wall. You don't have to use Larson trusses, so it's a quicker construction method. You are kind of limited to stucco on the outside, but that is also a cheap construction method that can result in lower expenses for the habitat climate. We're going to use 36 inches of cellulose in the ceiling. And in the green boxes, those are the inputs that you have to put in. Everything else is calculated. We're using triple pane windows that represent the best triple pane windows that Zola manufactures. We're using one door, and you could also have a second door and a sliding glass door on the south. That's kind of a good plan. We're using 0.6 air changes per hour at 50 pascals. The volume of the building is simple. It's just that square times the 8-foot ceiling height. And then also ventilation, that is actually the value that's used for my house. So we just put in that approximately 100 cubic meters per hour. And then also the ERV efficiency is input just as a nice round 90%. That may be a little bit larger than the actual. Internal heat gains assume 2 adults in the house 24 hours a day. Appliances, that comes from scaling our appliance load in our house. And then we put in an aperture that represents 5% of the floor area. And that, again, needs to be the net transparent area. So the frames can be quite a large percentage of the gross window area. So this number needs to be the transparent area. And with internal heat gains, this house being so efficient actually has a very small loss. It's quite a bit lower than the passive house recommendation. And then finally, just out of interest, the balance point temperature for this house is that it will remain comfortable indoors down to about 23 degrees Fahrenheit. It needs to get colder than that before you need any kind of heating, including from the sun. Thermal mass includes perimeter walls that are 8 inches thick and then a 4-inch concrete slab. We're also adding light construction for the interior walls and furnishings. Note that the walls are 62% of the thermal mass, and the concrete floor is 35%, and just a little bit from everything else. And then here's the main page. The one thing that we're going to modify from the calculations from the other sheets is that we're going to add 25% for thermal bridging. This is probably a conservative value where we don't have Larson trusses, but we do have thermal bridging in the roof trusses. But now we're ready to calculate hourly indoor temperatures, and here they are. So outdoor temperature is in the yellow or orange, and you can see near the end of January, we get down to minus 25 degrees C or minus 10 degrees Fahrenheit, and that corresponds with when the indoor temperature gets down to our lower comfort limit. Now, let's take a look at January. The first week, temperature is decreasing. We have a couple of weeks where the temperature is relatively constant. Then that fourth week, we drop down to that lowest temperature. The rest of the year, it's fully comfortable. Here we're going to show the value of those similitude parameters. We said that if we add SLR and ILR, and if it was close to 1, then the house would remain comfortable. For that first week in January, it's less than 1, so that corresponds to decreasing temperature. The second and third weeks, we're at 1 or a little bit more. That's where the temperature is relatively constant. And then that fourth week is that extreme event. The sum is less than 1 again, and we reach the lowest temperature of the entire year. The short green parts of the bars indicate that January is cloudy. So again, that's the worst part of the weather for the entire year. All the other green bars are thicker, so we've got more sun, and we've got that sum above 1 for all the rest of the weeks. Thermal time constant depends on outdoor temperature, and so it ranges from about 2.5 to 7 over the heating season. So I had a question during the registration period about more challenging climates. And in the next couple of slides, I want to show performance of a building that's 100% ambient conditioned in every climate zone in the US. And we're even including Fairbanks, Alaska, where we have almost 3 months of very little sun. Now, to get to 100% in Fairbanks, we need a lot of glass so that we gain enough heat in the summertime to bridge that long sunless winter. And so you can see that the maximum temperature where we have a low thermal mass passive house without opening the windows and without controlling solar gains, it gets to temperatures where you would actually cook inside. That you couldn't live in that house at all. If we include the controls, then we reduce the overheating considerably. But when we add thermal mass to make it an ambient house, the green bars show that we are remaining comfortable even in Fairbanks, Alaska, with the right amount of thermal mass, the right amount of solar gain, etc. Other challenging climates include Phoenix, Arizona, where for 50 days in the summertime, the nighttime temperatures are above the thermal comfort limit. So let's take a look at the actual values. So in the first column, these numbers for the envelope loss coefficient just correspond to meeting that passive house limit of 10 watts per square meter. For the area of solar gain to floor area, 5% works in a lot of the climates, but note that in Fairbanks, we have to go to 30%. So that's why that house overheats so much when we don't control the solar gains. The ventilation to load ratio is the third column, and 10 works for a lot of the locations, but Miami in particular is the highest one, 10,000. That is much higher. We're not going to get that value with natural circulation. It's probably going to take forced circulation and a lot of surface area in the thermal mass to make this work. Internal heat gains to envelope loss for the winter is high in Phoenix, and that's mostly because the envelope losses are low, but otherwise, the internal heat gain to load ratio is within a pretty narrow range. Let's skip over to the thermal mass, the MCCP over A, and remember that this range was in the 100 to 500 range for conventional construction, and a lot of these buildings are. Los Angeles needs very little thermal mass to be 100% ambient conditioned. But there are exceptions. Let's talk about some particular examples. First, Atlanta is not terribly challenging. With ventilation cooling, we need a value of 420. That's near the high range of conventional construction. But if we use sky cooling, we can reduce it to 260. That's kind of in the moderate range for conventional construction. And the last two columns show the amount of concrete, the cubic meters per square meter of floor area, and the amount of water that would be required. Phoenix, that's one of the most challenging climates, and for Phoenix on the heating side, note that for ventilation cooling, we need 14,000 kilojoules per square meter per degree Kelvin, but with sky cooling, we can reduce that down to about a third of that much, but it's still a very high value. You need to have a lot of thermal mass in Phoenix to get to 100%. Fairbanks, perhaps the most challenging climate, we actually need a little less thermal mass than for ventilation cooling in Phoenix, but it doesn't matter whether we're using ventilation cooling or sky cooling. In Alaska, the evenings get plenty cool, and we can use either method to keep the house cool. The constraint is more on bridging those 3 months of cold and sunless winter. And here for Phoenix and Fairbanks, so we need a meter or 1.5 meter of water under each square meter of floor. That's like a wading pool worth of water. And in Europe, some buildings are using storage like that and usually combined with active solar systems to try to get close to 100%. Okay, so to wrap up this part of the presentation, let's think about what are the guidelines that we can learn from these designs. So first, these guidelines are very similar to Norm Saunders' versions from the 1980s. First is super insulation. We need to be thinking about 2 to 3 times more than the code. Norm Saunders' house was 2 to 3 times more than those very early codes that were just developed in the 1980s. And now that's closer to code value. For my house, for instance, if I remember correctly, the R value for the walls that's required in the code is around 27, and we have 73 in the walls. So that's in the range of 2 to 3 times more than the code value. Solar gains, we need quite a bit less than the old passive solar buildings, and 5% works in a lot of areas. You note that my house is actually 4%. Thermal mass, moderate to heavy conventional construction value is a lot less than the old passive solar buildings. And here's some numerical values that is a good place to start. We also need to control solar gains more in some climates than others. Overhangs can work well in some climates and then in others. And if you don't have room for an overhang or it just doesn't work out, you can use shades that are manual like mine or automatic ones. And we also need to incorporate and control either nighttime ventilation or sky cooling in climates that need cooling. And finally, we want to remember that we need to use a dynamic model. The monthly load models are not appropriate for ambient houses, and we also need to use ambient meteorological year weather data that currently you have to develop yourself. It's not necessarily difficult. You just have to do 20 or more annual simulations with real weather data to develop that AMY data set. Okay, in the last several slides, I want to talk about why this is important and make the point here in this slide that we need ambient energy to meet our climate goals. Right now, the Energy Information Administration says that we will only be down to 44% fossil-derived electricity by 2050. That's not going to meet our goals. At the same time, built floor area is expected to double by 2060. That makes the problem bigger. And on-site PV is increasing at a very rapid rate, but right now it's just the tiny little light green cap on the top of our total building energy use. And by 2050, it's going to be just a little bit thicker, but still small cap on total energy. So these columns represent all of the energy used in buildings if we were to suddenly electrify all of the buildings. The black and gray are the direct fossil fuels. And if we increased efficiency going to a overall coefficient of performance or COP of 2, of course, we would cut energy use in approximately half. If we expand out to 2050 and we have converted some of our electricity to renewable sources and we have more on-site PV, but building surface area is almost doubling, we're at about the same fossil fuel use as now. If we increase COP to 2, that's the fourth column, then you can see we still have about a third of the fossil fuel used in buildings as we do now, but it's only when we use ambient energy for these several applications that they're good at supplying that we get to really close to zero fossil fuel use. So we need ambient energy to meet our goals. Ambient conditioning is also cheaper. The cost of an all-renewable electric grid has been estimated to be between $8 trillion and $21 trillion, and the lower estimates tend to neglect the increase in buildings and expanded transmission, and storage costs are a big problem because we're not sure, for instance, that batteries is the best solution. Also, if we electrify all buildings, we end up with a large peak that's 3 times greater than the minimum in the wintertime if we're heating all of the buildings with electricity. That means we need a lot of overcapacity or a lot of batteries or some combination of those. If instead we think about ambient conditioning these buildings, right now heating and cooling is about 25% of the total building energy use, or rather not of actually the total, not just for buildings. If we divide that by the number of buildings, we come up with a value of 14,000 to 50,000 per building just for heating and cooling. And think how much insulation and better windows you could add to your house with that amount of money. And then you wouldn't have any energy bills associated with heating and cooling. So, for instance, Jim Riggins' house back in 2011 cost just $5,000 extra to get to almost 100% heating and cooling. You can see that that is 3 to 10 times lower than the estimate for providing that same energy from an all renewable electric grid. So ambient conditioned buildings are also more resilient. The green bars you can see are definitely increasing. Those are the severe storms that could result in an electrical outage. A conventional building will respond when the electricity goes out relatively quickly and can even get dangerously uncomfortable indoors, where an ambient conditioned building doesn't need electricity to remain within a comfortable limit and can remain comfortable indefinitely. So it's a safer building. Ambient conditioning is also lower carbon. Now, there's been an emphasis recently on an embodied carbon, but we need to remember that operational is still the larger part of total building carbon. And often a small investment in embodied carbon can reduce operational carbon a lot. And that's typical for an ambient conditioned buildings. Heat pumps have high embodied carbon that ambient conditioning can eliminate. And kind of the signature feature of heat pumps is the refrigerant. R410A, for instance, is 2,000 times worse than CO2 in the atmosphere. And even its replacement, R454B, is 500 times worse than CO2 in the atmosphere. Energy storage in concrete is also about 10 times lower carbon than energy storage in batteries. That concrete will last for a century or perhaps more, where we need to replace the batteries even after we've spent a lot of carbon creating the batteries. Cellulose insulation is one of the best insulations that you can use because by some accounts, it actually has negative CO2 equivalent. So the more insulation you put in your house, the lower embodied carbon it has. Ambient conditioning also promotes energy equity. So several facts here. Heating and cooling of buildings is a big business. So half of about $500 billion is spent annually on utility bills. Low-income houses have an energy burden, and that is about 3 times larger than the average. And that makes the energy bills difficult to pay. In 2023, almost 20 million US households collectively owed about $20 billion in unpaid utility bills. So the utility bills are already a problem, and they're only going to increase. In 2020, about 27% of households in the US tolerated unsafe indoor temperatures without air conditioning, which ambient energy could supply, either because the air conditioning unit didn't work, or they didn't have one, or they couldn't afford to turn it on. Half of that $8 to $21 trillion amortized over 10 years for the number of buildings in the US gives us $240 to $630 just for the capital expense of creating that renewable grid per building per month. So this is an extra added charge that everyone, including low-income households, would have to pay just for creating our all-renewable grid. And ambient energy can reduce this by half just for heating and cooling, and then we have hot water and other applications as well that could reduce it even more. So last slide here. I think of our current national energy strategy as being very supply oriented on doing everything with electricity. It's like telling this little girl, sorry, sweetheart, you can't eat all of that bread because we have to be conservative with what the bakery will sell us when we're surrounded by a field of wheat. We have ambient energy all around us that is free for the taking, and why not use it? So thanks to all the audience, and thanks to Brett and everyone at Greenhouse or Green Home Institute for hosting this webinar.
Yeah, thank you so much, Keith. And now we're going to jump into some questions that have come up. Before we get to those questions, just a real quick reminder that yes, this session is being recorded. Yes, you can rewatch it, catch anything you might have missed, share it with a friend, colleague, post it on social media, help us get the word out. Please, you can wait a couple days and head over to Green Home Institute, our YouTube channel down there to see it, or you can go there now, click subscribe. You'll get an instant update when it's available. For those of you watching this in the future, not right now, on demand, you can take the quiz with an 80% passing rate and receive your continuing ed certificate. For those of you here today, as long as you've been here the entire CU approved hour with the name in your Zoom account that you want written on your certificate, take that survey that pops up as well, and you will receive your CUs and certificates. Check your spam from certs@gutenbergcerts.com. And as those questions are coming in, a huge thanks to our board of directors, our volunteers, our executive director, Jose Reyna, our nearly 400 supporting members. We're almost there. We need to get to 400 by the end of the year. So if you haven't signed up for your membership, do that now. I'll drop a link in the chat. Help us get there so we can keep doing this work next year. And a huge thanks to our top tier sponsors like Rheem for decarbonization of water heating, Build Equinox for energy efficient, demand controlled ventilation, Panasonic Mitsubishi Climate for more resilient buildings to earthquakes and wind, and Timber HP for reducing embodied carbon within our materials. So, Keith, you talked a lot about ambient energy at the end there, helping reduce the stress on our grid, and clearly all data points that electric use is growing exponentially no matter what we do to reduce demand. It is growing and growing, and as we shift to electrification, it's going to grow more. But the reality is, most of the infrastructure we have has already been built. So how do we do ambient on our existing structures? And what thoughts do you have on that?
Yeah, certainly there are challenges for some buildings in incorporating ambient energy. For instance, you may be right next to someone on the south side, so you don't have good solar access. That creates a problem. You can use glass on the roof to get light into the house. In many cases, there's still a way to get around that. But if it's difficult to get solar gains, then at least you can do more insulation. Make it like a passive house, which emphasizes lots of insulation and excellent windows. In some cases, you can reduce losses by 90% there. And that makes a lot of sense. We really should be looking at remodeling a lot of our houses. I forget the exact numbers, but if every major remodel of buildings in the US were to include these energy retrofits, we would reach our goal before 2050. There's a lot of remodeling that is going on right now. And if everyone did the energy modifications, then it would really help in reaching our goals.
And I guess maybe if you have some knowledge, where is the biggest pain point? Is it the passive solar gain for us up here in the cold climates in the winter, where we, have a lot of opportunity for existing homes? Or is really more, is it for those down in the warmer climates, is it going to be easier for them to focus on passive solar to keep the sun out and stop from overheating and energy uses in the summer? Like where, if you had to like pick one, where would most of the passive solar beneficial efforts go in existing buildings?
Oh, okay. Well, really, I think for retrofit buildings, the big barrier may be getting thermal mass in the building, and that works
Yeah.
both for heating and cooling. If you have a slab on grade house, it may not be insulated around the perimeter, but that's something that you can do. You just have to dig out around the house and place some insulation in there. It's not quite as good as having insulation under the slab, but clearly that is way more difficult. Um, and then the question about, is heating or cooling more difficult?
Oh,
Well, like Phoenix, it's 50 days where you just can't use nighttime ventilation. It's just too hot at night. So
yeah,
that is maybe the great challenge. Almost everyone can have solar gain on the south side. If you can't, then I feel sorry for you, but it
yeah,
doesn't take a lot of solar gain. But some places you just have very limited nighttime ventilation. Now, for
yeah,
sky radiation, you can't go out and just buy sky radiators like you can solar collectors. So that's
right.
more of a do it yourself kind of thing. You may need an
Yeah,
engineer to help design it. It can be done. And I wish we had some product development to attack that problem because it would
yeah,
really help in the warmer climates.
yeah, yeah. Um, the other thought that kind of came up, and I was thinking the question was kind of in my mind as you were showing off your comfort in your home. And I was kind of waiting for you to show us a dew point chart because quite, honestly, if we're really talking about comfort, dew point is really the number we have to be looking at least in my opinion. You could be it could be, 78 degrees, but what is that humidity? That's really going to, change your opinion on comfort. So, can you speak to us a little bit about your own personal experience with dew point or what your thoughts are, with controlling dew point in homes like this?
Yeah, right. That's something that we didn't cover very much. There was that one slide where I referenced um, Zach Springer's paper on doing dehumidification with night sky radiation. So, I
Yeah,
mean, there's some problems with that because we don't have sky radiators yet.
yeah,
There's very little work so far on how the rest of the system to do a dehumidification with ambient energy, but that certainly is um, a barrier in some climates, although I don't think it's as large a barrier as you might imagine, because we only have to get the air down to 57 degrees so that when it warms up to interior temperature, it's
mm,
at a low enough relative humidity. So I
yeah.
think that's a problem that can be solved, and we need some people to attack that problem.
And just in your own personal experience, did you track your own dew point, or can you just anecdotally say, you know what, it wasn't humid in my home, at least in the on the cooling side anyway.
Yeah, so I'm in a dry climate in
Oh, okay.
Colorado.
Yeah,
When it's snowing outdoors, it can be higher humidity, but that's really cold. And so
sure.
that cold air, when it comes in, it's going to be at a comfortable humidity. And
Yeah,
I have recordings of humidity, but it stays around 30% for most of the year. So it just isn't an issue here.
yeah. Yeah, good point. And I guess maybe on the flip side, then it'd be the other side of the coin, it'd be the dry air, right?
Yeah, yeah. So the ERV exchanges some of that moisture, and so
Yeah,
it's pretty darn close to 30% for the
yeah.
entire year.
And that was the other question I was going to ask you about your ERV. Are you running at a certain ASHRAE standard? How do you have it set up?
Oh, yeah. So the person who sold us the ERV recommended a larger unit than perhaps the house needed. And so we set it on the lowest conventional setting. There may be some special settings where you could reduce it even more.
Okay.
But we are at about 100 cubic meters per hour, I think it is,
Yeah.
um, of ventilation. That was like the setting number one for
Mm.
ventilation.
Yeah.
And so we haven't done anything special to change that.
Do you
That ends
track?
up being
Go ahead.
uh, a few percent of the overall loss of the building.
Right.
So, it's good that we are doing heat recovery
Right.
because if we weren't at 90% efficient, then that percentage would be large compared
Yeah.
to the overall loss.
And do you track CO2 or VOC metrics to see if they're in line, or are you just letting it run and assuming it's ventilating as it should?
Yeah, yeah, not yet. We
Yeah.
plan to get a CO2 monitor just to check and see, but I
Yeah.
think it's probably fine.
Yeah. So you brought up at the end embodied carbon, and I'm glad you did. Of course, when we think of passive solar, and the questions that came over, we in your own house, we think of all this, concrete, the cements, the things that really pull in high embodied carbon. So,
Right.
can you speak to that? The trade-off is the trade-off for ambient energy that we have to use all this high embodied carbon in the materials to achieve these goals on at least new construction homes, or what are your thoughts on that?
Yeah, that's a really good question. In our house, we have a slab on grade for the basement, which almost everybody would use anyway. It's very conventional. We have concrete perimeter walls around the basement, which is also conventional.
Mhm.
You kind of need that in order to hold back the ground in the walkout basement.
Yeah.
The one thing that we have added that is different, not quite so conventional, is a 4-inch slab for the upper floor. So that's extra concrete that you'd have to count against embodied carbon. But the extra concrete that we have has a payback of about 3 years. So I mentioned investing a little embodied carbon to get a large reduction in operational carbon, and that's an example of that. That three
And if do
years
you
includes
go ahead.
the extra polystyrene, which also has some embodied carbon.
Right.
Um, we needed to use polystyrene where the insulation could get moist, like the
Mhm.
underground parts on the lower floor. So I'm counting that too in the 3-year uh, carbon payback.
Right. Um, and uh, the thing I was going to ask on the embodied carbon side uh, as well was, well, do you know if because there are more, cements, concretes, and forgive me for getting them interchanged here, but I do. They can come with more lower, more greener alternatives, we'll just put it. There are many different innovations. Do you know if there are trade-offs when that occurs? That then displace that don't allow that concrete cement to be as good for thermal performance? Do you know when they reduce the embodied carbon? Have you heard anything like that?
Oh, so the thing where you get the most embodied carbon in concrete is in the Portland cement,
Right.
which is the smaller fraction of the concrete. It's probably 25% or less than the total concrete. Most of it is gravel and sand. Um, concrete is high embodied carbon, and there are ways of reducing that Portland cement um, embodied carbon. And I don't know, as the few papers that I've looked at have
Mhm.
said that the strength of the concrete is just as good as the high embodied Portland cement. So there are other ways to reduce the embodied carbon of concrete as well that I haven't seen anyone talk about. For instance, you have to cook the Portland cement to get it to be Portland cement, and you could
Mhm.
use solar energy for doing that. That would be a great application of thermal ambient energy. Um, Lots
Yeah.
of things could be done.
Yeah. Um, so another question that came specific to your home is is the ground loop air or glycol in your house? It sounds like it was a glycol solution, right?
Yeah, it was a glycol solution because the
Yeah.
liquid flows through the ground and it's not going to freeze in the ground, but when you're
Right.
drawing in outside air across the heat exchanger, need to make sure that liquid doesn't freeze and crack inside the
Yeah.
house.
Yeah. Um, what are your thoughts on ambient approach for those who live near bodies of water? So someone here mentioned, of course, being near Lake Michigan, that's different than the ocean, but just in general, just being near bodies of water, does that alter how you would approach this?
Yeah, so I think being near a body of water often causes more cloudiness, so your
Mhm.
solar gains are going to be lower. Um, it in most cases means that you're going to need more thermal mass.
Yeah.
I noted that Mark Challam is watching, and he says that Adobe and compressed earth is a way to have low embodied carbon. And
Hmm.
so that is a way that you could
Yeah.
incorporate a lot of thermal mass in the house with lower embodied carbon. But
Yeah.
being near a body of water sometimes means that the temperatures are more moderate. I mean, that makes it simpler, but it can also lead to more cloudiness. Think of
Sure.
Seattle, for instance, a lot of
Right.
cloudiness. I think we needed to increase the ratio of solar aperture to floor area to 15 or 20%
Yeah.
in Seattle to have enough solar gains.
Yeah. Um, so it's interesting you brought up these dynamic models, and I start to think about the how we've had to move our energy modeling tools to hourly kilowatt usage to get prepared for time of use programs. So I kind of think of that in the same way that we also need to move to almost an hourly basis. I've personally used the PV Watts calculator to look at, my hourly energy use predictions as well. So it seems like we need to move to this more granular approach. You mentioned, and I may have missed it, I said on your tool, you said that we need some more uh, updated government weather data, and you said you'd explain that later. And somehow I may have missed that. What is it that we're looking for that then would allow us to have more weather information that would be needed?
Yeah, so it's that finding the years with the most extreme winter and the most extreme summer. So
Uh-huh.
right now, weather data set that I'm calling an ambient meteorological year is not available. You have to develop it yourself. It's not
Okay.
necessarily difficult. You just have to do 20 or more years of individual simulations and then look
Uh-huh.
at the results to see which winter and which summer is the worst. Then you take those winters and summers and put them
Uh-huh.
together into 1 year of AMY data, and then that's the end of that task. You can use that same data set for that location for any building you want to design.
And is that you said something that is under development by the National Weather Service or the federal government or somebody, or was that something you heard is being put together?
Yeah, it's not yet. And so far,
Uh,
I only have about five data sets that I have done. I
yeah,
did those four locations that I showed a slide for, and then I've done Pagosa Springs
yeah,
also. But
okay,
someone, it would be a really simple problem because you could automate it
yeah,
and run all those thousands of locations around the US
yeah,
and get all the results.
yeah,
But it's a matter of having someone do that.
yeah,
Um, and it would be great to have it archived right there at the National Solar Radiation Database.
yeah. Well, it may not be a priority coming up at this point, I would
Yeah,
imagine. But
right.
maybe an institution or a state government wants to take it on. So that would be interesting. But that was kind of getting to the point, like, so we people could theoretically utilize your resources and your tool. They just need to then go out and kind of do this extra research to have that information that's missing, correct?
Right. That's what needs to be done now. And
Yeah.
if
Yeah.
anyone is interested, please let me know if you are a really good programmer and you could do some of these calculations. Let me know. We'll get together, and there
Yeah.
are other places that we could archive data. It
Yeah.
doesn't have to be at the National Solar Radiation Database. In fact, if there was an
Mhm.
archived set of data somewhere that could kind of push the NSRDB to do the archiving, then that might be like a first step.
Yeah, interesting. Well, and real quick on that, you're talking about going into the past, but the future is going to be very different than the past. We're already breaking records here, on heat especially, but even on cold. So how do you compensate for the future that is going to be very different than the past? Where does climate predictions and modeling come into this?
Yeah, so that's a really good point. Uh, right now, the AMY data sets I've used are from
Hmm.
past data up to the current most
Sure.
recent data set, but we really want to project those, say, 60 years into the future. That's kind of
Right.
the usual lifetime of a
Yeah.
building that's used for simulations and predictions. And there are ways of doing that. Um, uh, Sometimes they're really simple. We just add a single value, but there are some other ways of projecting to the future that add some randomness. And those more sophisticated models are probably the better ones.
Yeah.
And maybe someone listening knows more about it than I do. But yeah,
Yeah.
we really should be simulating with future weather data.
Right. Well, someone here's got some homework, so reach out, let us know. Please help us out,
Absolutely.
whoever that might be. But Keith, we are at our time. I appreciate you sticking over a little bit longer and doing another session for us. I really learned a lot, and I hope everyone else did. So I'm very grateful. I'm gonna have to go back and watch it again, to be honest, so so I can digest it a little bit better. But on that note, again, where can people, if they do want to reach out to you, go to contact you and learn more?
I'm at keith.sharp at Louisville, as in Louisville, Kentucky, .edu.
All right. Keith, thank you so much for your time. Have a great holiday season. Be well, and hopefully we'll be in touch otherwise. So, and thank you all. We'll see you next week. So, goodbye.
Thanks, Brett. Thanks to Green Home Institute.
Be sure to check out all of our courses available online that you can watch anytime and anywhere to pick up your CEUs. Before you go, make sure to subscribe to us on YouTube to get weekly updates and stay up to date on green building science courses, webinars, and home tours. Thanks again.